from the Miau Corporation. I'm chairing the first session, which is focused on optics. The first talk of the session is Oliver Cossairt, Daniel Miau, Shree Nayar from Columbia University. And the title is Gigapixel Computational.
Okay, so that was a great talk that was great, and I'm going to follow it up talking about Gigapixel cameras. Yeah. Thank you. Okay, that's what I thought. Okay, so this is work done at Columbia University on Cossairt, work done with Daniel Miau and Shree Nayar, and funded by DARPA and NSF. So today we can go to sites like gigacam.org, and we can see these gigapixel images that were captured by scanning a low-resolution camera across a larger field of view. And it'll show some really stunning examples there. This is just a random example that I picked off the Gigapixel site. And I should thank you for doing a much better job than I could ever do motivating why you would want gigapixel images. But basically, from my point of view, what's really stunning about these images is that you can zoom in and you can see so much more detail than was visible by the naked eye at the time of capture. So what I'm going to talk to you about today is how do you capture these gigapixel images in a single snapshot with a single camera. And Illa talked to you a little bit about this awesome new time-lapse, time-warp technology. And really what we're sort of thinking towards is, can we create a single camera that can do single snapshot gigapixel images, that sort of thinking towards actually doing gigapixel video. And I'm not actually going to talk about gigapixel video here. I'll just talk about the gigapixel cameras. So why is it that you can't just go to a store today and buy a gigapixel camera? Simple question, but we'll just look a little bit closer into this for now. And so the first question you might ask is it because of sensor resolution? And but we know that CMOS sensor manufacturing technology has advanced to the point that we can produce sensors with pixels as small as 1 micron. And when we have 1 micron pixels, we can actually fit 1 billion pixels onto a relatively small sensor package, something like a 40 by 25 millimeter sensor. So it's within the capability of today's sensor technology to manufacture these gigapixel sensors. Of course, no one is doing it right now, but it could be done. So really, the limitation right now is not sensor technology. The limitation is due to the optics of these cameras. So that's what I'll be talking about mostly today. So let's look a little bit closer at optical resolution. And so, okay, so an ideal lens creates a perfectly focused image. Real lenses don't focus perfectly. For real lenses, the spot size, the minimum spot size that can be produced from a point source is limited both by diffraction and geometric aberrations. The space bandwidth product of a lens that just means how many of those individual spots we can fit within our image size. And that just is just what we think of typically as optical resolution. And so for the rest of this talk, I'm just going to sort of use space bandwidth product and optical resolution interchangeably. So the diffraction from the aperture of the lens limits the minimum spot size that we can get from the lens. And when we stop down the aperture and increase the F number, we increase the amount of diffraction, increase the spot size due to diffraction. But the spot size depends only on the F number. So what that means is that if we scale up our imaging system uniformly so that the aperture and the focal length scale up by the same amount, the F number doesn't change, so the spot size doesn't change. So if when we're scaling up our lens, we keep the same field of view. We've just scaled up our entire camera, scaled up our lenses, our aperture, and our sensor. We're actually able to increase resolution because we're able to fit more spots within a larger image size. And so from this, we can just very easily derive that a scaling law for diffraction-limited lenses, which just says that the resolution increases with the square of the lens scale m. And so this law tells us that basically if we have a diffraction-limited lens that's at f2, then we can image 1 billion pixels with a relatively small sensor. In fact, we could have used that 40 by 25 millimeter gigapixel sensor that I talked about before. But unfortunately, in general, lenses are not diffraction limited. So in practice, what mostly limits the resolving power of lenses is geometric aberrations. And this is just because, in general, there's no actual optical surface that can produce a perfect focus for all points on an image. So, so basically, we're limited by the shape of the lenses that we can produce, how good of a focus they can get. And aberrations scale linearly. Geometric aberrations scale linearly with lens scale. So that if you scale a lens by a factor of 2, the geometric aberrations scale by the same factor. So what happens when you try to scale a lens that has geometric aberrations is what you see is that for smaller scales, the diffraction is larger than geometric aberrations. So resolution does increase with lens scale. And then what happens is that you get at some scale where the geometric aberrations are larger than diffraction, and then you reach this plateau in resolution. And what's happening here is that after you get to this point, geometric aberrations are dominating diffraction, and then your geometric spot size is what's affecting your main lens spot size, and that's increasing with the same scale of the lens. And so what that means is when you double your image size, you're also doubling your spot size, so you can't fit in any more image spots in the image, and your resolution plateaus at some point. And then I'm throwing up these equations for the scaling laws. These laws, you can go back to Lohmann's paper or my paper. I won't go into any detail about these equations. I'm just showing them here for completeness. So aberrations, the amount of geometric aberrations always depends on the aperture size of the lens. So you can always stop down the aperture of a lens to decrease the amount of aberrations. So you increase the F number, and your aberrations go down. Most people who are, played around with these SLR cameras are pretty familiar with this property that if you stop down the F number, you can get sharper images. And so a typical rule of thumb that's actually used in lens design in a lot of cases is that the F number is typically set to be the cube root of the focal length in millimeters. And this is just sort of an empirical rule that lens designers use that's actually followed pretty closely across a lot of different camera lens designs. And this was something that Lohmann talked about in his '89 paper about the scaling laws of lenses. And so he used this empirical rule to derive a scaling law for sort of conventional lens design that says that basically it encompasses how lens designers break the aberration limit by trading off optical efficiency for reduced spot size. And so again, what's happening here is that when we're scaling up our lens, our aperture is decreasing. And so when our aperture is decreasing, we no longer have this aberration limit where we're plateauing resolution. And that's because as we increase the spot size, as we increase the lens scale, we're stopping down our aperture, so our spot size isn't increasing by the same factor as our lens scale. And so when we do that, basically when we stop down our aperture, when we increase our F number with scale, then we can break this aberration limit. And in fact, there's a good deal of designs that follow this empirical scaling law that Lohmann discussed, going from microscopes to telephotos. And what the scaling law tells you is that if you want to image at 1 billion pixels and you're on this Lohmann line, then you need an image size of about 400 millimeters. And that's exactly where these large format cameras that a lot of us who've been to these ICCP talks have seen. Last year we saw a talk by Moshe Ben Ezra about Microsoft's DG Cam. He used an a Schneider aposimar lens, which produces an image size of about 400 to 450 millimeters. I think the actual full circle image size of that lens is defined to be 500 millimeters. And then I guess it was the first ICCP, and if anybody was here, we saw Graham Schmidt, showed us his images from his asymmegon lens that are produced for the Gigapixel project. Again, so these lenses use large format lenses. Graham Schmidt uses a custom lens that he designed, this asymmegon lens, but in principle it's a similar design to the large format Schneider lenses. And the idea is that you have really large image sizes and really large f numbers. And so your image sizes are typically about a factor of 10 larger than your image size for an SLR, which you can see here the scale factor by looking at the SLR that Graham Schmidt's using for viewfinding for his gigapixel camera. So we're actually proposing a different approach. Our idea is to use a very simple optical element and to capture a blurry image, and then to use deblurring as a post-processing step to recover a high-resolution image. And the idea here is to try to use computations to reduce the complexity of the optics, and it's an old idea dating back to some of the cubic phase plate work that Kathy and Dowski did. Ed Dowski's going to give a talk later. I guess it's not about this sort of thing, but basically they looked at infrared imaging systems reducing complexity for infrared imaging systems. And some other researchers have sort of looked at this same idea of how do you use computations to reduce complexity. So, and we're trying to push this idea to the extreme. We're actually going to do imaging with, maybe the simplest optical element, which is just a spherical ball lens. The idea of using spherical optics is actually really old. We didn't come up with that idea. It dates back to about 150 years to a Sutton ball lens. And then in the 40s at Harvard, Baker looked at some spherical optical designs. And then more recently, Christian and Nayar looked at designing a spherical field of view, single viewpoint camera using just a ball lens and a computational imaging approach. But their design requires this custom spherical sensor that is beyond the reach of today's manufacturing technology. And then Marks and Brady just recently proposed this Gigagon design, which is a relatively complex design. It uses 6 concentric spherical shells. It's a relatively complex design, but it's also extremely high performance. It can actually image up to 40 gigapixels across a 120-degree field of view. It's an f2 280 millimeter focal length lens. So what our main contribution is we analyze how the resolution scales with lens size for a computational imaging system. So specifically for a spherical optical system. And what's really unique about these spherical optical systems is that they produce images onto a spherical image plane, and as a result, they're completely symmetric. So you don't have any field-dependent aberrations. The point spread function is completely identical for all points on the image plane. And the only aberrations that you have to really worry about are spherical aberrations and chromatic aberrations. So basically what we do is we look at this computational imaging system with just a ball lens imaging onto a sensor. We scale up the optics and the sensor, but we make the pixel size stay the same. So now our sensor is able to fit in more and more pixels as we scale up our optical system. And then because geometrical aberrations dominate in this optical system, as we scale up our lens, our PSF size, the support of our PSF is actually increasing linearly with the scale of our lens. And then the real observation that we make is that even though the PSF scales linearly, that the deblurring error scales sublinearly. In fact, it's extremely sublinear. When you do a fit to this curve, you actually see that the deblurring error scales with the fractional power of the lens scale. So this is a really interesting observation. PSF scales linearly, deblurring error doesn't. So basically, you can play with this equation for the deblurring error, and I won't derive it here, but in the paper you can go and see that we can use this equation for the deblurring error that was fitted to come up with an equation for how the resolution for a computational imaging system scales with lens scale. And the really interesting thing is that this new equation for the scaling law for computational imaging outperforms the Lohmann scaling law for conventional imaging. And what that means is that if we want to image at 1 billion pixels, we can do it with a much smaller image size. We can do 75 millimeters instead of 400, 450 millimeters. So to demonstrate this principle, what we propose is to image with just a ball lens onto an array of 15 by 15 5 megapixel half-inch luminaire sensors. And the idea here is that the array of 15 by 15 sensors closely approximates the spherical surface, so that even though we're using planar sensors, the PSF doesn't vary significantly across the position on each individual sensor. As a proof of concept, we built a system to emulate our proposed design, which just uses a ball lens and a single sensor. And the idea is that the single sensor is scanned sequentially to multiple sensor positions using a pan-tilt motor. And the idea is that for static scenes, this system would capture exactly the same imagery as a complete system, which uses 225 different sensors. So here's the image that would be captured by a single sensor. Again, you can see it's a low contrast image, but there is high frequency details because of the shape of the PSF actually does preserve high frequencies. And then when we deblur, we can get back to high contrast and we can get a lot of details, high frequency line pairs, checker pair patterns. This is not as good quality as a diffraction limited lens, but it's really remarkable quality considering we're imaging with just a single ball lens. So I'll show you some examples that were captured with our prototype system. I'd have to switch real quick to Gigapan. I had some trouble getting this to work on my Mac. So first example I'll show you is this is a still life scene. It's about 50,000. Do you remember the resolution? 50,000 by 40,000 resolution. Actually, let me see. Sorry, it's 82,000 by 20,000. It's about 120 degrees field of view across. And here we're zooming in to a flower. And when we zoom in far enough, we can actually start to make out that the individual weaves of fabric on the lens. We can make out that this is a fake flower. And then we can zoom over to a dollar bill that's posted on the other side of the room. And this image was captured at about a meter distance. And when we zoom into the dollar bill, we can actually make out the individual stipple patterns on the dollar bill. And then when we zoom down to a remote control in the bottom right corner, we can actually make out some ridges in a fingerprint pattern there. We could actually probably even do fingerprint detection on that. So here's another example of the New York skyline. This was taken from Governor's Island. Downtown is about 6 kilometers away. So let's see, first off, I guess we'll zoom into some boats that are hanging out down in the Bowery near the ferry docks. And if we zoom in far enough, we can actually see a person walking on the boat of that on the deck of that boat. We can zoom out and move up to the Empire State Building, which is about 6.4 kilometers away. You can make out the tip of the Empire State Building. And then finally, we can zoom out and we can see something that was totally invisible when we're looking at this completely panned out view. We can see an airplane flying in the corner of the sky. And this was, of course, something that we discovered much later. We had no idea that this was up there at the time. So let's see. Okay, so those are some example gigapixel images. We have another example of a portrait scene. You can go onto Gigapan and you can see these examples. We have them posted. But the previous design had one slight problem, which was that is really a practical issue, which is that when you try to pack these sensors really close together, you run on with issues. Basically, you can't get the active area of each sensors to be perfectly abutting. There's no practical way to do that. So that one way that you can get around the issue is actually you can create multiple systems with slight shifts in orientation, and then that allows you to fully cover the field of view. Another way is what we show here is that you couple each sensor with a secondary lens that slightly adjusts the field of view so that you create overlapping field of view between adjacent sensors, and you create a fully contiguous view across the entire system. And the idea of using a secondary relay lens with a sensor to enlarge the field of view from the perspective of the sensor and create a contiguous field of view was first proposed by Brady and Hagen in their multi-scale lens design paper. And also, I should mention that there's a parallel effort using very similar ideas by Brady's DARPA Mosaic team. But here we're actually presenting a slightly unique design. Instead of using the secondary lenses as relay lenses, they're actually acting as focal reducers, and they're made of the same material as the main ball lens. And so what that allows us to do is actually manufacture a single, the entire optics out of a single element, and we do that by actually molding an array of relay lenses onto a spherical surface of a ball lens with the same material. And then the idea is that, of course, you would have a spherical shell of sensor arrays that would fit around the optics to complete the entire system. And this is a design that we're currently pursuing, exploring. So, okay, so we do gigapixel imaging with just a ball lens, low complexity, low complexity, but lower performance. And now Marks and Brady proposed this gigagown design, which is also a spherical optical system, which is high complexity, but it's also really, really high performance. And what we're really interested in doing, and what is ongoing work for us, is exploring this trade-off between complexity and performance. And now, the idea of creating a quantitative measure for complexity for a general lens design is actually really difficult, because you have all these things like you could have aspheric lenses, how many degrees, polynomial are you using for your aspheric lens, and so on. But for spherical lenses, it's relatively simple. The idea is that basically, if you want to find the next degree of complexity greater than a ball lens, well, you add a shell around the ball lens. So now you have two spherical surfaces, each of which has 2 degrees of freedom, the radius and the glass type. And it has one constraint, which is that we want it to have the same focal length and F number and field of view across all degrees of complexity. And so we basically go into Zmax, and we plot these variables in Zmax, and then we find the optimal lens design, and that tells us the best possible performance we can get for the next degree of complexity greater than just a ball lens. And then we can repeat this for 3, 4, and 5 shells, and we have this sort of discrete notion of complexity for the spherical optics case. And then we can look at the MTFs for these lenses, and then as we expect, the MTF for the 6 shell case, the Marks and Brady's gigagon design, is close to diffraction limited, and then we lose performance. The MTF gets worse as we reduce complexity, and of course, as the MTF reduces, the deblurring error, if you're talking about a computational imaging system, would get worse as well. The deblurring error would get greater. So, here we're plotting the actual deblurring error. We're plotting the signal to noise ratio after deblurring for these spherical shell optics relative to a diffraction limited system. So a diffraction limited system would have an SNR of 1. And what's really interesting here, so there's two interesting things that I want to point out here. The first is that when we go from 1 to 2 shells, we get about a factor of 19 or 20 increase in signal-to-noise ratio. So that's a huge jump in signal-to-noise ratio for a really small price to pay and increased complexity. The second thing is that when we go from 2 shells to 4 shells, we only get a factor of 4 increase in signal-to-noise ratio. And so, depending on the application, that a factor of 4 increase in signal-to-noise ratio may or may not be a significant enough improvement to warrant going from a 2-shell to a 6-shell design, where we have a lot more difficulty in aligning the elements and a lot more expense in manufacturing the elements. Either way, what we think is really interesting is that by charting out the space of complexity versus SNR, what we've allowed the lens designers to do is essentially pick the lens design with minimal complexity that meets their SNR budget. So that's space that we're ongoing work, and we're really interested in this. So just in conclusion, I showed you a new scaling law for computational imaging that improves upon this Lohmann's scaling law for traditional conventional lenses. I showed you a gigapixel computational imaging camera design that uses just a ball lens and an array of planar sensors. And then I showed you some example gigapixel images that were captured with our prototype camera system. And then I showed you a single element design that creates a fully contiguous field of view for a given sensor array. And then I told you a little bit about this idea that we're exploring now, which is this trade-off between signal-to-noise ratio and complexity. Okay.
Are there any questions? Okay.
Very interesting topic. So I have two questions. First of all, if you have a single element versus multiple elements, how does this affect chromatic aberration?
Yeah.
And second question is just a basic question. How difficult is it actually to make speed?
So if you have a single element, your chromatic aberrations are pretty bad. I can't remember the exact number in the shift in focal length between colors for just the ball lens, but it's not very good. What we were depending on there for the single ball lens cases that were essentially that humans are less sensitive to color blur. So actually, in those images that you saw, the example images that we captured with the ball lens, there is a lot of chromatic aberrations. You just don't notice it so much. When we're doing this optimization across different levels of complexity, we're taking chromatic aberrations into account. So that MTF plots that we showed is actually the MTF including chromatic aberrations. In terms of the complexity, I don't know too much about lens manufacturing. I know that I can tell you that we were able to produce these ball lenses. We had them custom manufactured, and we're looking at doing multi-shell designs. And in terms of the people that we're talking to, they don't seem to have any issue with going, as long as you're not talking about fully spherical designs. So we have to actually no, they were okay with that too. So there's issues with when you go with the fully spherical design, it's actually clamping, figuring out points to mount onto mechanical parts and stuff like that, which is an issue when you're making the lenses.
All the designs you showed had 120 degrees field of view.
Yeah.
Is it possible to reduce that field of view?
Yeah, no, actually, this is discussions that we've been having with Ravi. And I think that's one of the next things that we're going to be looking at. In a lot of cases, what you're really interested in is this, your instantaneous field of view, right? Is you want to have a small instantaneous field of view as possible. And so when you're looking at really large field of view systems, you're not necessarily minimizing your instantaneous field of view. What you really like to do is have as small a field of view as possible and still have this resolution. So obviously, yeah. So I haven't looked too closely at this. I'm really interested in this question.
What last?
Yeah. Yeah. That was not a log, so the question. Oh, sorry. Do you want to finish your question?
Yeah, so I was wondering how to log scale instead of the language, what kind of relationship.
So the question was about the complexity versus SNR plot. And it's just a linear scale, so you can just take the log of the values, and that would be the log of C. The SNR is computed directly from the MTF.
Okay, well, let's thank the speakers once again. The next talk in the session is titled Validity of Wigner Distribution Functions for Ray-Based Imaging. Yesterday you heard an entire long presentation about the phase-space optics. So for those of you, this should be a very interesting talk. The authors are Tom